All right, welcome to the video on uniform circular motion. We are now entering Unit 8, and this is going to be the first of 3 videos in the series. And just to warn you a little bit, this first video is going to be a little bit more lengthy than the other ones, because uniform circular motion, we need to make sure we lay good groundwork. This unit has the potential to be confusing, even though it actually is a very simple concept. So we want to make sure we do a good job understanding the concept behind circular motion, so that way when we do the math and we do the problems, it'll be a lot more simple. So without further ado, let's go ahead and get started. When we talk about uniform circular motion, it's a good idea to start about what we talk about or what we mean when we say the word uniform. Uniform just means constant or same throughout. And what that means is we're looking at uniform circular motion meaning uniform speed or constant speed. So if we look at this blue particle orbiting around this red center, we would say that it's moving at constant speed. Now, it's been a while since we've talked about the idea of speed. In fact, it's been since first semester in Unit 2. So let's go ahead and revisit just real briefly. When we talk about speed, speed is a scalar quantity, and speed is found by taking the distance something goes over time. And remember, distance is ground traveled. So, for example, if I went 10 feet north and then 10 feet east, I would have gone a distance of 20 meters, never mind the fact that I went north first and then east. Now, when we're looking at a circle or something moving in a circular motion, the same thing applies. However, our distance needs to be a little bit more specific. So when we talk about what distance an object is going in terms of circular motion, we're talking about its circumference. And so we're going to calculate circular speed by taking the circumference the object moves divided by time. Now notice circumference, just like distance, is measured in meters, and so your units for speed will still be meters per second. Now let's look at the equation that develops. You'll see that it has a v in the equation. Let's not be confused. Even though it says v, we're really talking about speed here. We're not talking about velocity. We'll talk about velocity in just a moment here. But when we use the equation 2 pi r over t, we are really calculating speed. Now, 2 pi is a constant. The letter r represents the radius that the object is moving, and the radius does need to be in meters. So if it is in centimeters or any other kind of meter, we'll need to convert that. And then at the very bottom, you'll see a capital T. Now, a lot of times students think that that's time, but it's not. It is measured in seconds. However, the capital T is representing the period. And the period represents the amount of time it takes the object to move in a circle one time. And so if it takes this blue object, let's say, for example, I don't know, 10 seconds to get around the circle once, 10 seconds would be the period. And that's important to know. So make sure when you're doing the equation to find speed, you are dividing by not time, but specifically the time it takes to get around one circle. All right, now I told you I would talk about velocity and speed, and that's what we're going to do on this slide right here. So we talked about how uniform circular motion is a constant speed. However, the velocity is changing. Remember back in first semester we talked about how velocity is a vector quantity where speed is scalar. So speed, it does not matter what direction it's going, but velocity, it does matter. And obviously, if you look at a circle, the object is actually constantly changing its direction. Otherwise, it wouldn't be moving in a circle. And so since the object's direction is always changing, even though its speed is constant, its velocity is changing. Once again, it's changing not because it's speeding up or slowing down, but simply because it's changing its direction. Now, in the animation that you see, you'll see 2 arrows. You see an arrow that is pointing directly towards the center, and then you see an arrow that is pointing kind of like out to the side. First of all, let's notice that the arrow that's pointing towards the center has the letter A, which you could probably guess stands for acceleration. We'll talk about that in just a moment. But I want to focus on the arrow that is labeled V. And V stands for velocity in this case. It stands for velocity because it has a vector, it has an arrow, and so it has a direction. And you'll notice the direction is always changing as it moves around the circle. Now, what's important to note is that this object is moving in a circle, but let's say the object was somehow expelled from its circular motion. Which direction or which way would the object fly? And it's important to note that it would fly in the direction that the velocity is pointing at that particular time. This is what we call tangent velocity. Okay, and we call it tangent velocity because we are talking about the object is moving in a tangent direction. And excuse me, I need to just get this in here. Sorry about this. There we go. Sorry about that. All right, tangent velocity. And if you've taken math, you should hopefully remember that the word tangent means touching the circle at one point. So the tangent velocity, or we sometimes call linear velocity, is the magnitude of the velocity at that particular time, and it's facing the direction in which is tangent to the circle at that point. So the velocity is always directed tangent to the circle at any point in time. So you can see that represented in the animation over and over and over again. So to get a better idea, let's just actually do a simple little problem here. I have a circle and it says an object is moving in uniform circular motion from point A to point D. And we're talking about point A to D as if it has to go through B and C as well. So it's moving in a counterclockwise direction. The question wants us to draw the velocity vectors at each point. Now notice it just wants velocity vectors. It doesn't want acceleration vectors, it just wants velocity. And we learned on the last slide that velocity is always going to point tangent to the circle. So at point A, the velocity is going to be tangent to the circle. And notice there that I have the velocity drawn tangent to the circle at that point. So if the object were to be let go at point A, it would actually just travel in a straight line to the left. And actually, it would continue traveling in a straight line unless some other force acted on it, like, for example, maybe gravity. Okay, let's go ahead and do point B here. Point B is directly on the side of the circle, and so it's still moving in a counterclockwise direction. So tangent to the circle would just be straight down. At point C, it's at the very bottom of the circle, so tangent to the circle would be straight to the right. And then you notice D is kind of on a little bit of a diagonal. It's not fully to the side, it's not fully up or down. And so drawing a tangent there would look something like this. And so the key thing there is that if the object were to be let go at any of those 4 points, it would follow the paths that are represented in blue. And, you know, we can just keep doing this for an infinite amount of points on the circle. It doesn't even matter where I draw. So if I wanted to know what's the tangent velocity at that point right there, I would just draw a tangent line and make sure that my line is straight. Okay, so that's tangent velocity. So the circle, the object that's moving in a circle is always going to have a velocity that is pointing in the direction that is tangent to the circle at that point. Now, I didn't do a great job of this in the drawing, but it's important to note that since we're looking at uniform circular motion, meaning constant speed, all the lengths of these arrows are actually all equal to each other, indicating that the speed is not changing, but just simply the direction. All right, now the next thing we want to look at acceleration, and this one can be a little confusing if we don't remember what acceleration is and how we find it. And so that's what this slide is right here. We are going to revisit acceleration in a linear form, and then we're going to apply it to a circle. So you might remember back from Unit 3 or first semester physics that acceleration is simply a change in velocity over change in time. And that's what those little triangles stand for. They stand for the Greek symbol delta, but all that means is just change. So change in velocity over change in time. Now, if I expand out what change in velocity is, all that is it's final velocity minus initial velocity. And anytime we're doing a change in something, whether it be change in velocity, change in momentum, change in time, change in volume, whatever it is, it's always final minus initial, not initial minus final. So final minus initial is there. And then finally, when we are looking at vectors, for example, this is a velocity vector, we always do what's called vector addition. We don't do what's called vector subtraction, we do vector addition. And so since we do vector addition, what I've done is I have rewritten the top part to be, instead of v final minus v initial, it's v final plus and then negative v initial. So mathematically, I haven't changed anything, but I've now written it in the form of vector addition. Now you're probably wondering, why do you do that? What's even the point of that? Well, let me show you. Let's take a look at this first example on the very top. So the red arrow, the red velocity vector, is going to stand for my initial velocity. And the blue velocity vector is going to represent my final velocity. So we're looking at just a linear example here. Notice the arrows are pointing in the same direction, so we're not looking at a direction change, but we're looking at a magnitude change, meaning a speeding up or slowing down. So from the image, from red to blue, hopefully you can see that the object is speeding up. I know it's speeding up because the blue vector is longer than the red vector. Okay? And so it's speeding up, and therefore my acceleration, when an object is speeding up, my acceleration vector must point in the same direction as my velocity vector. That's what makes it speed up. Now, we've always accepted that, but I'm going to show you how we actually solve that mathematically. And we're going to use my vector addition that's up here. So what we're going to do is we are going to take my final velocity, which is representing the of the blue arrow, and we're going to add to it the initial velocity. But notice the initial velocity has been turned negative. And if you know anything about vector addition, or remember anything about it, we know that when you put a negative in front of a vector, it flips it. So since there's a negative v initial, I'm going to take my initial velocity and I'm going to flip it so it has the opposite direction. Now when you add vectors, you add them tip to tail. So I'm going to add the vectors as the tip of that arrow matches up with the tail of this arrow. That's how you add vectors. You do tip to tail. So when we put those two vectors together, our resultant vector, the one that's left over, is going to be the difference between the two, or whatever is left over. And that's this part right here. Now, will this part be facing to the left or facing to the right? Well, in other words, is our resultant vector facing the left or the right? Well, which arrow was bigger, the blue one or the red one? The blue one was clearly bigger, and so my resultant vector is going to be facing to the right. And this makes a lot more sense if we actually gave numbers. So let's say I said the blue vector was 10 meters per second, where the red vector was 3 meters per second. So we could see my resultant vector would be 7 based off of math. We were subtracting because the arrows are facing opposite directions. Okay, so we were able to prove that the acceleration points to the right. Let's do one more so we are feeling confident with this idea. Okay, so in this one, we still have initial velocity is represented in red, and we're going to have my final velocity represented in blue. All right, so before we do our vector addition, let's predict what direction the acceleration should be pointing. We can see from the arrows they're getting shorter. And so if the arrows are getting shorter, that indicates that the velocity final is slower than the initial velocity. So the object is slowing down. And for an object to slow down, the acceleration vector has to point opposite the velocity vectors. Okay, once again, this is a review from first semester, so I'm hoping this is not new information. But if it is, we're still learning. But now we're going to figure out, can we prove that the acceleration actually does point left? And so we're going to do our vector addition again. We're going to do v final plus negative v initial. So I need to add to it the flipped version of my red vector. Now I'm going to add them tip to tail again. So the tip of the blue arrow, I'm going to line up with the tail of the red vector. So just like this. And then the result is going to be, just like before, the leftover between the blue and the red. Now, which way will it point? Well, which vector was larger, the red one or the blue one? And in this case, the red one was larger. And so since the red pointed to the left, so does the green. And now we have proved that the acceleration is indeed pointing to the left. All right, now that was a linear example, and the reason why we needed to do the linear example is so that when we did the circular example, it would make sense. So now we're dealing with an acceleration, a change, or in other words, a change in velocity that is not coming from speeding up or slowing down, but of changing direction. And so we're going to do that the same way, but our result is going to be a little different. So from the previous slide, remember, acceleration is just change in velocity over change in time, which, remember, change in velocity is v final minus v initial over change in time. Or that's the same thing as v final plus the negative of v initial over change in time. Okay, so now that we know that, I'm going to take my final velocity vector, which is right here, and I'm going to add to it the negative of my initial velocity vector. And what we're ultimately trying to find is when the object goes from this point on the circle to this point, during that motion, where's the acceleration pointing? Now, you might remember, oh, from the animation a couple slides before, I remember acceleration always points towards the center. We're going to prove that right now as to why that is. All right, so I'm going to take my final vector, and I'm going to add to it the negative of my initial vector. So I'm going to flip this left to right. Next thing I'm going to do is I'm going to add them tip to tail. I can get my vector. There we go. I'm going to add them tip to tail just like that. And so now the resultant is not one-dimensional, but in fact it's two-dimensional. In other words, it's going to complete the triangle. Okay, now the question is it going to point up or is it going to point down? And sometimes students have a really difficult time with this. They don't know if it points up or down. And so I try to think about it like if you were to mix these two red vectors, if you were to mix them together, what would you get? Well, the horizontal vector right here, the horizontal vector doesn't have any vertical characteristics, if you will. It's just left or right, and we know it's looking left. And so since it's all horizontal, there is no vertical. However, this vector right here has components of horizontal and vertical, meaning it goes a little bit to the right and also a little bit down. And so since it's the only vector that has vertical components to it, when you draw your resultant, my resultant must also face down. Once again, it has to face down because this vector right here also face down. I sometimes give the analogy of if these two vectors were making a baby, it's kind of weird, but if they were making a baby, you know, the mom has horizontal genes only, the dad has horizontal and vertical genes, and the vertical genes are down. And so your baby vector, which is right here, has to also have down genes. Okay, and so what have we really realized here? What have we come up with? Well, what we've come up with is that when we do our resultant vector from vector addition, our change in velocity, or in other words, our acceleration, is pointing down and to the left. And if you kind of line that up, look where it points. It points towards the center of the circle. So it doesn't matter which 2 points on the circle you would have chosen, you will always get an acceleration that will point towards the center of the circle. All right, I'm actually going to split this into 2 videos because this is a little long. So we will go ahead and see you in the next video.